Hey everyone. So, you ever see a chart or a table packed with data, but you don't have the original raw numbers that went into it? It happens all the time. Today, we're going to tackle a classic stats puzzle. How do you pull real insights, like an average, from data that's already been grouped up and summarized? I mean, think about it. You've got a frequency table showing, say, age groups, but the actual individual ages are gone. So what do? Just throw your hands up and say it's impossible? No way. There's a method to the madness. And that's exactly what this explainer is all about. We're going to dive into some really powerful techniques for estimating the center and, the spread of data, even when it's all clumped together. It's kind of like being a statistical detective. Okay, so let's jump right in with our first and probably most intuitive tool, the weighted mean. Seriously, this concept is the foundation for everything else we're going to cover. The best way to think about this is your GPA in college. An A in a big 4-credit stats class should probably count for more than an A in a little 1-credit seminar, right? Of course, that's a weighted mean. The weight is just the number of credit hours, which gives more importance to the tougher courses. Now, don't let the formula freak you out. The idea here is actually super simple. For each thing you're measuring, like a college course, you just multiply its value, the grade, by its weight, the credits. Then you add all those products up and divide by the total of all the weights. Let's see it in action. Okay, let's actually do the math with this GPA example. First up, English. An A is 4 points, and it's a 3-credit class. Multiply them together, you get 12. Next, statistics. A B is 3 points, but it's a 4-credit class, so that's also 12. And finally, history. A C is 2 points for 3 credits, which gives us 6. So you can see our total credits, our weights, add up to 10, and our total weighted points are 30. So what do? We take that total of 30, and we divide it by the total credits, 10. And boom, our GPA is a 3.0. See, this isn't just a simple average of the grades. It's a weighted average that gives us a much more accurate picture of performance. All right, so we've got the weighted mean down. Now, let's build on that. What happens when our weights aren't credit hours, but are actually the frequencies in a data table? This is where we shift from doing a straight-up calculation to making a really clever estimation. This is the big question, right? If we know, say, 12 people are in the 20 to 29 age group, what specific age do we use in our math? We can't just pick 20 or 29. That would totally throw off the result. We need a single value that can represent the whole group. And the solution is to make a really smart assumption. We use the midpoint of the class. So for a group that goes from 10 to 19, our best guess for where the data clusters is right in the middle, 14.5. This whole idea, this midpoint assumption, is the absolute key to this entire process. So let's apply this. The frequency is now our weight, and the midpoint is our value. It's just like the GPA example. For that first class, we multiply its frequency, 5, by its midpoint, 14.5, to get 72.5. We just do that for every single row, and then we sum up those totals, exactly like we did before. We take our grand total of 642.5, divide it by the total number of data points, 25, and we get our estimated mean, 25.7. And notice I'm saying estimated. That's why you'll often see that squiggly approximately equal to symbol. It's a really good estimate, but it's still an estimate. Okay, so finding the center of our data is awesome, but it's really only half the story. We also need to get a feel for how spread out the data is. Are all the numbers clustered tightly around that mean we just found, or are they kind of all over the place? That's what standard deviation tells us. So to put it simply, standard deviation measures consistency. If you have a small standard deviation, it means your data points are all huddled together, close to the average. A big one means they're much more scattered and varied. Now, this calculation might look a little hairy, but it's really just a sequence of logical steps. We take each midpoint and subtract the mean we just calculated, 25.7. Then we square that number to make everything positive. And finally, we multiply that result by the class frequency. That gives us the weighted squared distance from the mean. The key is that last column. We add it all up and get the number we need, 1,264. Okay, hold on. Before we get the final answer, we have to ask one incredibly important question. Is our data the entire population, or is it just a sample of it? Because that answer changes the math just a little bit. For a whole population, you divide by the total count n. But for a sample, you divide by n minus 1. And look at that tiny change actually makes a difference in the final result.
This is such a brilliant insight. The formula for a sample is designed to give you a slightly bigger standard deviation. It's like a built-in statistical penalty. It basically acknowledges that since you don't have all the information, there's more uncertainty. So it gives you a more conservative and often more realistic estimate of the actual spread. It's pretty cool.
So after all that, what is the one crucial thing we absolutely have to remember? It's that these techniques are incredibly powerful, but we can never forget their one big limitation. Since we started without the original, raw data, our answers are always going to be approximations.
All right, let's do a super quick recap. When the raw data is gone, we have to estimate, plain and simple. We use those class midpoints as our best guess. The frequencies then act as the weights, just like in our weighted mean. And the most important thing, our results are always powerful approximations, not perfect exact values.
And that really leads to a final, bigger thought. We live in a world of big data, where we're often chasing these perfect, super precise answers. But sometimes a really good, fast, reliable estimate is actually more useful for making a smart decision. The next time you see a summarized chart, you'll know the secrets that are hidden right inside. Thanks for tuning in.